When you hear the word light, what's the first image that pops into your head? Most people would think of something along the lines of this bright, yellowish white stuff, like a lamp, a light bulb, or the sun. So is that what light is? Just this yellow, glowing luminescence? Is that really all it is? Well, my laser pointer points red light. What about that? And what about the rainbow of all different sorts of colors? Okay, so now we can define light as any different type of color luminescence. Is that all there is to light? Well, that's just what we see. But there is actually more to light beyond than what meets the human eye. There are all different types of light, some visible to us and some not. Light is basically this thing called electromagnetic radiation, and all the different types of light, all the different types of electromagnetic radiation are arranged in this thing called the electromagnetic spectrum, which is really just an array of all the different types of light. Similar to how we humans have a hearing threshold, we can only hear pitches between 20 and 20,000 hertz, we also have a seeing threshold. Some light is visible to us, and some light isn't. Wait a minute, hertz? Hertz is a unit of frequency, and I know frequency is a property of waves. Waves, well, I know there's sound waves, but if you're telling me that we have a seeing threshold just like how we have a hearing threshold, wouldn't that mean that there's light waves? Wait, light as a wave? That's right. See, when people talk about what light is composed of today, you hear the word beam and ray. But what really is a beam of light made of, and what really is a ray of light made of? So this guy, Thomas Young, decides to investigate. He sets up two boards, one directly in front of the other. For the sake of this video, let's pretend they're cardboard. And in the first board, he cuts two very, very narrow slits through the board, and they're close together to each other. And he sets up a laser pointer in front of the first board, so that its light can reach the two slits and go through them. So with this X-ray shooting out a red dot at the two slits, what would you expect to see? What we would have expected is that the red light that misses the two slits just reflects off of the first board, like this. And the light that reaches the two slits and goes through them continues to travel through them until it hits the second board and reflects off of the second board. And it would look kind of like this if you looked straight at it. More precisely, the second board, the back board, would just look like this. But this did not end up happening. What the backboard did really look like was this. The light had somehow spread out. How could this have happened? If light was a wave, then when it travels to the two slits, it would diffract through them. It would spread through them, like this. And they would keep spreading until it reaches the backboard. Notice how at some points the waves intersect. Focus on just this point right here, and look at the two waves that are intersecting. Now, as a wave travels a distance, its cycle is to go up, down, and then back to where it started. If you look at the two waves intersecting here at this point, notice that one came from the right slit and one came from the left slit. And the one that came from the right slit had to travel a little farther to get to that point. So they met at different points in their cycles. Now the wave from the right could have traveled a whole extra cycle to get to that point and meet the left wave. If it travels one full extra cycle, then the waves meet in phase, meaning their peaks meet together or their troughs meet together. This is called constructive interference, where the waves combine to make a bigger version of themselves. But if the wave from the right only traveled half of a cycle extra, then its position at that point where they met would be opposite of the other wave. So when they meet, they would cancel each other out in what is called deconstructive interference. There would be no wave at all there. So that occurs when the waves meet out of phase. So that explains why some spots on the backboard did have light, because there were waves there that constructively interfered. And some spots had no light, no waves at all, from destructive interference. The only possible explanation for seeing some bright and some dark spots on the backboard is that light formed an interference pattern and therefore acts as a wave. Since light is a wave, it can be described in terms of wavelength and frequency, and that is what differentiates all the different types of light on the electromagnetic spectrum. For example, the visible light region on the spectrum ranges from 400 nanometers to 700 nanometers in wavelength. Now let's talk about the photoelectric effect, which has to do with solid metals, say aluminum. If you shine some source of light on it, then electrons will somehow spontaneously be emitted from the metal. How does this happen if electrons are attracted to the nucleus of aluminum from the protons and want to stay in the metal? Well, clearly that means that light has to be composed of energy to make this happen. And this energy is carried in little packets called photons. The energy of one photon is described by this equation, where h is a number called Planck's constant, and nu is the frequency of the light being shown on the metal. Notice how the energy of these photons goes up when the frequency goes up from the equation. So where does this energy that comes from photons that come from light, where does it really go? Well, electrons need some minimum amount of energy to be pulled away from their nuclear attraction. That's called the work function. And then whatever energy is left over in the photon is completely devoted to increasing the electron's kinetic energy. It's contributed to the electron's velocity when it's leaving the metal, how fast it shoots out. So I know the photoelectric effect deals with metals, solid metals, but to get a better understanding, consider the case of one sole atom with the nucleus in the middle and shells around it, and two electrons on different levels. Now let's say you're shining light of the same frequency on both electrons. Which one do you think will come out at a faster speed? Well, to get the maximum amount of kinetic energy from a certain photon of a certain frequency, you need the minimum work function, the smallest work function. So then it really just comes down to which electron has the smaller work function, meaning which electron is easier to remove from the atom. That would be the one that's farther away because it feels a shielding effect from the core electrons, so it feels less pull from the nucleus, whereas the one that's closer to the nucleus has a greater effective nuclear charge. So the one that's farther away is easier to pull away. So when it absorbs that photon, only a little bit goes to the work function, but a lot of it goes to the kinetic energy. Whereas when the electron right near the nucleus absorbs a photon, a lot of the photon energy is devoted to the work function, and only some of it is devoted to the kinetic energy. So this is kind of what they would look like when they come out with relative velocity vectors. You can see the one farther away would go much faster. By the way, there's this equation, the speed of light equals frequency times wavelength. So solving for frequency, and then plugging frequency into the energy equation, you can also have energy in terms of wavelength, which is usually expressed in nanometers for light on the electromagnetic spectrum. And as you know, light on the electromagnetic spectrum, all the different kinds of light, they all have different wavelengths. That's what splits them up. Okay, now let's say you shine some light on this electron of a specific wavelength, and therefore a specific frequency. And let's say that this wavelength, it doesn't yield a great enough energy to remove that electron. The energy is below the work function, so the electron cannot come out. So let's say now you shine a lot more light, like a lot more light. Still of the same frequency and wavelength, but a lot more light. By doing that, you're increasing the light's intensity. You're adding more of it. Do you think now that you've added a lot more light, the electron can come out? The answer is no, and this answer completely went against the wave model of light. By adding more light, you would expect the amount of energy to slowly build up and accumulate like a wave. But it didn't. All that increased was the amount of packets of energy. And that's where the whole idea of photons came from the first place. Now, light is being described as this stream of packets, this stream of discrete particles instead of a wave. If there was light being shown that did have enough energy to remove an electron, then increasing the intensity would only increase the amount of photons, which would only increase the amount of electrons ejected, not the kinetic energy that they come out with. When I say light acts discretely, it means it's either here or here, nowhere in between. It can't be like a wave where it can be at any point. Light is quantized. It's discrete. It's a particle. It's kind of like a ladder or a staircase. You can stand on one step or the other, but you can't stand in between. The light either had a high enough frequency to remove an electron or didn't. Adding more of that light wouldn't do anything. This means that light is quantized. But the double slit experiment showed that it was also a wave. So light sort of acts as a wavicle, as a wave and a particle. And this dual nature of light confused physicists for years, and it, along with the fact that an electron could also be a wave and a particle, led to the world of quantum mechanics, something that is still a very mysterious puzzle today. Thanks for watching!